Hi, welcome back once again to the Sound of Science. If you are joining us because you want to know more about scientific experimentation and investigations, then welcome. If you are joining us because you happen to be my student, I'm forcing you to watch this video. Sorry about your bad luck. Um, Today's topic scientific investigations. So, how do we create them? Why is it important we follow the rules? And what is the scientific method? So that's what we're going to be looking at today. When considering an experiment, you need to remember that if we design our investigation well, then we'll be able to see how one variable influences another, what their relationship is. If we don't design our experiment well, then we're going to falsely believe there's a causation where none exist. So let me explain that. Causation means that one variable causes a change in another variable. Correlation is more of a coincidence. For instance, according to the data collected, global temperatures have been steadily climbing as the number of pirates have declined. Therefore, pirates must be responsible for preventing global warming. So we just need to bring back more pirates in order to prevent continued global warming. Okay, obviously, this is a really silly example, but I have the data to back it up. And what that tells me is that this is a correlation, not causation. This is that part of science where you've really got to use some common sense here. Nothing the pirates did affected global temperatures. So therefore they can't possibly be the cause for their reduction isn't the cause for global warming, despite the fact that there is a correlation. It's not causation. Or even better, I love this example. So, Internet Explorer, as we reduce the amount of Internet Explorer use, we actually see a reduction in murder rate, which is kind of interesting if you think about how slow Internet Explorer is, and what that might actually indicate for us. And I do believe that, slow internet speeds could probably lead you in that direction, but I highly doubt that the reduction of Internet Explorer is really the reason that murder rates had fallen during that period of time. So, because of all of this, this is why it's important to follow the scientific method and carefully plan your investigations to make sure that what you're looking at is really what you're trying to investigate. So, scientific method. What you're seeing here are the steps of the scientific method. And I can hear you already, but Miss Myers, the scientific method I learned has 6 steps, or it has 5 steps, or it has 12 steps. And you're all right. The scientific method is kind of fluid. Um, we think of it more as a set of guidelines, more so than it must be these steps in this order all the time. Depending on the question you're asked, or you're asking, or you know how you are going to have to research it, what type of experimentation you're going to use, or what type of observations you're gathering, you may find that some steps are more important than others. But all investigations need to use the spirit of the scientific method. Um, and you're always going to be starting in the same place, which is stating your problem. So, what do you want to know? Once you have your problem stated, you're going to research any components that might give you a better understanding of what you're asking and what might be the variables involved. Forming your hypothesis is incredibly important. This is where you define what variables you believe are responsible for changes in the study subjects. You are stating what you suspect to be causing a change. Now, after you have all of that listed out, stated, then you can perform your experiment to determine if you're correct or not. You're going to reach a conclusion by examining your data. And once you reach that conclusion, you can now share your results with others or repeat the experiment or both. And this allows scientists to verify your results. If you watched my previous video, then you learned a little bit about pseudoscience and why pseudoscience isn't very good at scrutiny. It doesn't allow for others to examine it. Okay, so The scientific method is really actually something we use in most problem solving situations. But typically we do it so fast that we don't realize that's what we've done. So check out the steps here that I've listed of playing a video game like Mario. Okay, I get it. This is not a high level game. I understand completely, but almost everybody knows about Mario Brothers. And so this was a really good example for me to choose. So if we list out the steps of figuring out what to do with a Goomba, then it's going to look something like this. Now, I want you to think back to the very first time you ever played Mario and you had never seen Mario before, okay? Put yourself in that position. So your steps would be something like this. I need to kill this Goomba. That's my stating my problem. I know I can usually kill this Goomba from squishing it. That's your research or maybe observation. If I jump on the Goomba, it will die. That's your hypothesis, and it's really in almost an if-then statement. Number 4, your experiment. I jump on the Goomba, so that's what you do. You perform the action. And then number 5, your observations. This game has one less Goomba now because I jumped on it. Number 6 is your conclusion. Jumping on the Goomba was the way to kill it. My hypothesis was correct. Number 7 gets a little tricky here because there you're going to do repeated trials or you're going to share it. Repeated trials was something that I always did playing video games because I usually would get killed by, one of those little turtle ducks that would come up a little bit later. But if you wanted to share your hypothesis and your conclusions with somebody else, you could text your friend, I killed my Goomba by jumping on it. And your friend responds with, that. So literally, you are hardwired to perform science. And that's just what you do. Every time you come up against a problem, you're doing the scientific method. Sometimes you skip steps. Sometimes you do the steps so fast, you're not stating them. You're not even, in a lot of cases, stating the problem. You're just thinking your way through it. And that's okay. Again, I just want to make that point. You're a scientist and you've been hardwired to do science. So make sure that you know these steps of the scientific method. Make sure you know how this works. You get the spirit of it so you can kind of recognize when a scientific study has been done correctly. This is your best defense against pseudoscience. This is the best way for you to understand whether or not the study that you're reading has been done accurately and if it's giving you good information. All right. Now, we're going to look at the parts of an experiment. So, the independent variable is what I change. Independent. I change the independent variable. It's what we're testing. The dependent variable is what responds to the changed variable. It's what we measure to determine if our hypothesis is right or not. Everything else in the experiment should be a constant, and so that's what we call them. It should all stay constant. The constants are the things that are the same for all groups. All groups. Keep that in your head. I want you to remember constants are the same for every single member of every group. Okay? If it has anything to do with whatever your independent variable is, it can't be a constant because it's not a variable. So remember that the experimental group is going to get whatever the special treatment is. That's specifically the independent variable in this case, what we're testing. The control group doesn't get that, or it gets whatever's normal for the situation. That's what we like to call the status quo. You're going to see it written like that or said that way. It's the status quo. It's the way things are supposed to be. Knowing the parts of an experiment is really important to determining if your experiment is set up correctly. This is really important part of what we do. So take a minute, look through. You can always pause the video here. You can look through and just make sure you understand what these parts of the experiment are. I am going to help you identify them on the next slide, but just make sure you know these. Independent variable, what's being tested. Dependent variable, what we're measuring. Experimental group gets special treatment. Control group doesn't. Constants, everything else. If it's not a variable, it has to be a constant. Like I said, pause the video here, make sure you understand these definitions, and then we'll move on to the next slide. Okay, so if you paused, welcome back. If not, then I'm hoping you understand them. So here's an example that I wanted to do with you. So let's practice. If goldfish prefer rock music, then they're going to swim faster. This is a simple hypothesis, right? One trick for figuring out your variables is actually to place your finger or your cursor over the word then. Once you've done that, if you look to the left, you're going to find your independent variable. If you look to the right, you're going to find your dependent variable. This is just a trick I picked up. So anything, whatever's to the left of the word then in an if-then statement is your independent variable. Whatever's to the right is your dependent variable. Whatever measurement you find to the right is your dependent variable. So this only works if you're given an if-then statement. So if you don't get an if-then statement, or you don't remember that trick when it comes time to do a test on this, then how else can you determine your independent and dependent variables? Well, the independent variable is going to start with the letter I, reminding us that it's the variable that I control. I control this variable. The dependent variable starts with the letter D because it's what determines if our hypothesis is right or wrong. That's going to be the measurement that we're taking in our results. When we report our results, whatever the measurement was that we took for the results is our dependent variable. And regardless of which method is right for you in this case, the type of music is to the left, and it happens to be the thing that I can control. Therefore, it has to be the independent variable. Swim speed appears to the right, and it's what I'm going to measure, not what I'm controlling. Believe me, there really is no way to control the swim speed of a goldfish. So that has to be my dependent variable. That's our measurement. To determine the groups, remember that the experimental group and the control group are going to be very different. It's going to be two different groups of subjects. So in every experiment, you're going to have at least two groups, one experimental, one control. You may have multiple experimental groups. You may have multiple control groups. It just sort of depends on what question you're asking. But you can set your two groups up in really one of two ways. The first is you can create identical conditions with very similar participants. So the subjects, in this case, you're going to get the same type of goldfish, the same age, you're going to keep everything else the same. And you can do it as two different populations of fish in two different tanks, but they're very similar to each other. Or you can set up your two groups by separating them by time. So you can measure the fish, their swim speed with rock music and their swim speed without rock music using the same fish. Just depends on how you want to set up your experiment. Okay. So in this case, to make it simple, let's assume that we have two different fish tanks with the same type, size, and age of goldfish in both. And both tanks are going to have the same temperature, and the fish are going to be fed in the same way at the same time. One group is going to have rock music played for them, and the other group is not, because typically we don't play music for our goldfish. So our experimental group is going to be the tank that's getting the rock concert. That's what I'm controlling. That's the independent variable in this case, the rock music. The other tank doesn't get a concert, and that's going to be our control group because, again, that's not what we normally do. We don't normally play music for fish. And then finally, those constants, those are going to be all those things that I listed that I told you had to be the same for both groups. Remember the temperature, type of fish, and so on and so forth. So here is all of that listed out. You see all your variables, groups, and constants for this experiment. But remember, the scientific method normally has another step, sharing your results and repeated trials or both. In this case, using many fish in each group is an example of repeated trials. We could also repeat the experiment again. Most scientists also make revisions to their experiment. So, this is the point where you would think about things you could do in order to improve your experiment. Perhaps allowing the control tank to listen to a different type of music to ensure it's not just the music, but specifically rock music that helps goldfish move faster or influences their swim speed. You might also consider if any conditions may have inadvertently influenced your experiment. Was the tank too small? Did you have goldfish that had issues that might have influenced their swim speed? All of these things are part of the revision portion of the scientific method, and it's important that you take all of those things into account. Okay, so I know I'm going through this really fast. Remember, you always have the option to pause the video, rewind, try again, um, look at it one more time, get your definitions again if any of that helps, okay? So right now, let's try a different experiment. And this time, we want to know if using green light will make plants grow faster. Again, you need to figure out what variable you're in control of. Can I control the speed at which the plant grows? Can I control the light color? To know if something makes a plant grow faster, what would I measure? Um, I need to split my plants into two groups. Which of these groups would be the experimental group that gets the independent variable? And which is the control group that gets what plants normally get, the status quo? And then finally, what things are we going to keep the same for both groups? So pause the video here and see if you can figure out what's our independent variable in this case? What's our dependent variable? What's our experimental versus our control group? And what's our constants? And so see if you can kind of get in your head what these different variables and constants and things are. And then once you've done so, we're going to go to the next slide and you'll be able to see if you're right or not. Okay, so take a look right here, and we're going to figure out if you got it right or wrong. So your independent variable in this case is the color of the light. That's what I can control. I control the light color. Your dependent variable is what you're going to measure to determine if your hypothesis is right or wrong. So in this case, I want to know if plants are growing faster based on the color of light. So the only way to check if they're growing faster is to measure how fast they grow, the growth rate. Experimental group are plants with green light. We don't normally give plants green light. And then our control group is going to be our plants with normal light because that's what normally plants do. Constants, anything we want to keep the same. Plant type, plant size, water, length, time in the light, a whole bunch of other variables that we are going to control to make sure they stay constant. And another note with constants versus control group, just remember that the control group is different than constants. Okay? Thanks again for watching, and I'll see you next time on the Sounds of Science.